So this is actually called a vector program, okay, for many reasons, because the variables are vectors. There's also a scalar variable t sitting over there, but I'm going to ignore that for now. Okay. Now I'm going to reformulate at least part of it as a semi-definite program. It's not going to be exactly the semi-definite program that we saw before, but it's going to be close enough that you can convince yourself that it is. Okay. So what you do is just relabel the variables. Okay. What I will do is introduce the matrix variable y, which is a symmetric matrix on n plus 1 variables. Okay. I'm going to call y for some weird reason. I'm going to start indexing from 0, right, all the way till n. Okay. Now what I'm going to say is that the entries of this matrix are variables like yij, right, at n3 I comma j. And I'm going to define how yij is defined on the basis of ui and uj. Okay. I'm going to relabel yij as ui transpose uj. Okay. And this is for ij is greater than 0. So notice that now with this relabeling, let me write it down as a relabel. I have still max over t. So when I say ui transpose uj is 0, what do I mean over there? I mean that yij is equal to 0. So some of the entries of this matrix are 0 for all ij that are not edges in the graph G. Right? Norm ui square equal to 1 just becomes yii equal to 1. Okay. And for I equal to 0 or j equal to 0, I'll take the inner product with C. Okay. So if I rewrite this with this definition, if I rewrite the vector program that was here, I get these linear way constraints on the variables, and that's all that there is, right? Yii equal to 1 for all I, y0j greater than equal to t. Subject to, and I claim this constraint comes, and I will describe it y here, y greater than equal to 0. Okay. And of course, here I put for all I, this includes I equal to 0, which ensures that norm C squared equal to 1. Okay. So this positive semi-definiteness constraints actually encodes the fact that y comes from vectors. Okay, you cannot just arbitrarily take yij's, but I should have yij to be the inner product of two vectors. Okay, why is this actually true? So in this program, so in this optimization formulation, which looks very much like a SDP, except for this extra scalar variable t, which is sitting in R, which is not seemingly subject to these constraints, but you can add it back into the matrix, increase the dimension by 1 and set one of the y, uh, that diagonal entry over there to be equal to t. You can always do that. I'm not doing it. I'll keep it simple at this point. I claim that why does y greater, y being positive semi-definite even make sense over here? Right? Why being positive semi-definite makes sense? Because if you recall, one of the definitions of positive semi-definiteness was that y being positive semi-definite is true if and only if there exists a matrix U such that y is equal to U transpose U. Right? So this is the definition of PSD. Right? But then I claim that you can look at the columns of U, or rather the rows of U transpose, actually the vectors U1 to U1. Right. And then the constraint that Yij is the inner product of two vectors is automatically imposed and equivalent to Y being positive semi-definite. Okay. So that's the reason that semi-definite programs are useful over here when we look at the theta function. Okay. So what I've shown is that the theta function is actually a semi-definite program. Okay. Any questions about this or even questions about what I've just done before? That's completely fine. Please ask me. So this may be a bit more, if you immediately are looking at this for the first time, it may think, what am I doing? We're writing an optimization problem. Why are we writing that? Why are we rewriting it? It's because the optimization view of things actually gives us a nice handle into how to handle these quantities. Okay. So the big claim that I've made here is that the theta function, or actually t is actually 1 over square root of the theta function. But if you can compute the optimal of this program, you'll get to know what is theta of g, because well, I just flip it, right? I do 1 over t squared, and I'll get like this. Okay, so both of these are equivalent. Okay. So the takeaway from the previous one is that the theta function value, or rather, let me write it like this: 1 over square root of the theta function of a graph is the optimal value of a semi-definite program. Which is another fancy word for an optimization problem that we know how to solve efficiently. So this is kind of the summary. Now, the question that you may ask immediately is, well, I can express 1 over square root theta of g as a semi-definite program. What about theta of g itself? Can I express theta of g as a semi-definite program? Okay, directly, so that, I write a semi-definite program and the value of that is theta of g. Yeah, let's just do that. Currently, it just seems like a curiosity quest, but it is going to be useful for us in proving the sandwich theorem. So this is SDP1. I've already discussed this. Okay, I'll write down the second one, and then we will try to answer why is the optimal of this equal to theta of g. It's not going to be an obvious one. Okay. So in fact, what I'm going to do is, like before, because the theta function is related to geometric representations and you have vectors, I'm going to write it as a vector program first. Okay, and then you can think of this as a SDP. So I look at the following. Uh, I look at the following optimization problem. It's going to look very different than what is there before. Okay, so again you have an n vertex graph G, and V is 1 to n. Okay, the variables here are the vectors un, each is in Rn. Okay, and T is in R. Okay, so these are all the variables. And if you look at this, it seems very odd, right? So first of all, in the previous, when you have an orthonormal representation for the graph G, right, typically the inner product between ui and uj for ij in E bar is actually equal to 0, whereas here I'm calling it equal to -1. Okay. Secondly, the ui should be unit vectors. Here the vectors are of length t minus 1. Like the norm squared is t minus 1. And thirdly, there's no mention of the handle c over here. So why is this even computing the actual theta function? Right? We're minimizing t subject to these quantities. So it's not obvious, but it actually does. Okay. The claim is that the value of this is actually equal to theta of g. I was planning to do a proof of this, but it's slightly involved because it requires two parts. Okay. So what I will possibly do is in 5 minutes tell you one part of it. Okay. And the second part, I'll just leave it out and you can look at the reference if you are interested in knowing the solution. Okay. So I'm going to call, let Z2 star be the optimal, okay, of the above optimization problem. Okay, and what we want to show is that Z2 star is equal to theta of G. Okay, that's what we want to show. Um, so we'll show this in two parts. Okay, so one thing that I've not explicitly done again is told you why this is a semi-definite program. But looking at the previous example, it should be obvious. You can convert it into a semi-definite program that is matrix variables by introducing Yij being ui transpose uj for all ij. Okay. So certain of the Yijs are set to be equal to -1. Certain Yiis are equal to t minus 1. Okay. And overall, the matrix has to be positive semi-definite. Just going to be. So it can convert, but for our purposes, since you're not going to do the full proof for now, it is fine to just leave it in its current form. Okay. Which is just using vectors. It's slightly more intuitive that. Okay, so you're looking for vectors u1 to un and t such that it minimizes this value. Okay, notice that the previous STP was a maximization one. This is a minimization one. It's kind of expected because the previous STP value was equal to 1 over square root theta. Okay, this I'm saying is exactly equal to theta. So I'm going to write it as a lemma. Okay. And what we'll show is one part of this. We'll not show the full proof, but one part that is possibly easier to describe, I'm going to do one side. Okay. So to show that theta of g equal to z2 star, let me just quickly write that again. I should have written it in this slide again. Such that ui transpose uj is equal to -1, and for all ij in E bar, and what else do we have? Norm ui square is equal to t minus 1. Okay, so this is my optimization problem, okay, which I claim is SDP. The variables are p in R and ui is in Rn. Okay, so the first claim I want to make is that Z2 star, which is the optimum of this, is actually at most theta of G. Okay. Now, how would you actually find this? You know, how would you do this? So notice that Z2 star is a minimization problem, right? Over here. Z2 star is the result or the optimal value of a minimization problem. And therefore, what I will do is I'll start with the optimal orthonormal representation for theta of G, right? And using that, construct a feasible solution to this optimization problem. Okay, and if I construct a feasible solution to this SDP or vector program, if I construct a feasible solution to this vector program, then I'm done because the actual optimal value of the vector program will only be less than that. So what is the feasible solution we can construct? Okay, now notice that suppose I start with orthonormal representation for the graph. And the handle is C. Okay, so it gives the value theta of G if you look at the value of the orthonormal representation. There's a that is, sorry, maximum of 1 over C transpose Ui squared. That's equal to theta of G for this. So now what is the vectors that I will define which give you a solution to the semi-definite program? Now, just for clarity, what I'm going to do is I'm going to rename these vectors as V's because I'm already using U's as my optimal orthonormal representation. Okay. Such that I'm going to just call this V. Otherwise, there'll be too many U's floating around. Okay. So now here's a feasible solution. So let me call this optimization problem as SDP2. Okay. The optimization problem is basically the following. I set the feasible solution is going to be defined by the following. I'm going to define Vi to be C, the handle C over here, minus Ui by C transpose Ui. Okay. So these are my vectors which are feasible at this point. Okay. So I've given you a feasible solution, but I have to prove that it's feasible. I will let you do this as an exercise for the most part, but just note that suppose I take an ij that is an edge, that is a non-edge. And I look at Vi transpose Vj, this is what? Well, you get C transpose C minus C transpose Ui plus Ui transpose Uj by right, you get something like this. But because ij is in E bar, this last term goes to 0 because it's an orthonormal representation. And I get this is equal to C transpose C unit norm vectors. So this becomes equal to 1 minus 1 minus 1, which is equal to minus 1, which is what we wanted here. Right? So Vi transpose Vj is indeed equal to minus 1 for me. So this looks like a feasible solution. I'll let you verify the other constraints that is true. Okay. And I'm not going to show the next part that's slightly more involved to show that you can go the other way around also. Okay. That Z2 star from optimal SDP solution, you construct a orthonormal representation. Okay, of at most the same value. So you can go the other way also. I'll skip the proof for lack of time. Okay, so I have around 15 minutes. So hopefully I'll be able to finish the proof of the sandwich theorem, assuming this. Okay, so till now, what have we done? We saw an optimization formula formulation for the theta function. Okay. And in fact, the second optimization formulation is what we are interested in. Okay. And our goal was to show, well, if you remember the sandwich theorem, it was a structural result that said the theta function is sandwiched between the value of the chromatic number of the complement graph and is at least, let me just, omega of g bar, the clique number of the complement graph. This one we had shown already yesterday because omega of g bar is this alpha of g. And this was what we wanted to show. So what we did is that we found the optimization formulation, and now we're going to relate that optimization formulation to a coloring in the complement graph. And that's how we'll be showing that theta of g is less than equal to chi of g. Okay. So to show that theta of g is less than equal to chi of g bar, okay, this is what we want to show. Our proof strategy is going to be the following. You look at the graph G complement. Okay, recall that theta of G, the optimization formulation, is a minimization formulation. Okay? So I'm going to show that if G complement has a K coloring, a proper K coloring, okay, of the vertices. So I'm not going to define K coloring again. Okay, if G complement has a proper K coloring, then SDP2 that I've written has a feasible solution with value at most K. Okay, the optimization formula, which means theta of G is even less than equal to K. That's what it means. And therefore, this will show that theta of G is less than the chromatic number. Any K coloring you take. So in fact, you can take the optimal K coloring for that is K, the coloring with the optimal K, the smallest K, and use that, and you will get that theta of G is less than equal to K. Okay, so I've written this in the matrix form, but let me write it in the vector form. The matrix form is basically the following. The vector form. So Yij is just the inner product between Vi. Okay, so that's all there. So these are the only constraints. The variables are of this optimization are Vi's and T. These are vectors. Vi's are vectors and T is a scalar. Okay, so this is exactly equivalent. Now, how do I relate it to a coloring in the complement graph? Right? What does a coloring do? A coloring basically looks at whatever the graph, if you're looking at a coloring of a graph, right? Then adjacent vertices should not be assigned the same color. Right? That's what we have. Now, there is something, now when you're looking at the complement, of course, you have to look at non-adjacent vertices should not be assigned the same color because I'm looking at chi of G complement. Now, if you look at this, right, it says that there are vectors such that Vi transpose Vj is -1 in the complement. So can I somehow get colorings into this? Even colorings are edge-based criterion, this is also an edge-based criterion. Can I somehow get colorings into this? Okay. So how do we relate this to colorings? Yeah. So what I'm going to introduce is a notion of a vector K color. Okay. And I'm going to say that if a graph has a K coloring, it surely has a vector K coloring. That is an assignment of vectors to vertices, which has some coloring like property. And this is going to be the main thing that's going to help us. So let me write down the definition of what a vector K coloring is. So I know what a K coloring is, or I'm only talking about proper colorings, of course. So let me just write it down explicitly. It's an assignment. Let me call the assignment as chi. Okay, so chi of any I gives me a number in 1 to k, which is the color of that particular vertex, such that for all ij in for clarity, let me just call this as G prime. Okay, it's different from because I'm looking at the complement graph. So E prime is E complement. For all ij in E prime, chi of I should not be equal to chi of J. This is a K coloring. Okay. Now, what is a vector K coloring? How am I doing on time? Will I have 10 minutes? So a vector K coloring is basically an assignment of vectors to vertices. So I'm going to call that unit vectors. So let me call that by gamma, which goes from V to say Sn minus 1. But notice that currently there's no notion of K coming in here, and it will come in soon, such that for all ij in E prime, the inner product between gamma of I and gamma of j should be equal to minus 1 over k minus 1. Somewhat odd. What does this mean, right? So you have vectors for the vertices instead of usual colors. But what this is saying is that if uh, I and j is an edge, then those vectors should be at a certain angle. And that angle is actually obtuse. Okay, it's not acute. It's like minus 1 over k minus 1. Okay. So for instance, example, suppose say k equal to 3. Okay. So k equal to 3, what does this mean? Right. K equal to 3, this means that gamma of I transpose gamma of j should be minus 1/3. Or sorry, minus half. So which means if you have an edge between two vertices, its vectors should form an angle of 120 degrees. Okay, this is for 3 coloring. Okay, so instead of saying that in the scalar sense that chi I is not equal to chi j, okay, you are saying is that those vectors, the corresponding vectors should be kind of far apart. They should not be together. Okay. Now, why is this useful for us? Because what we are going to do is to show that if a graph has a k coloring, then it surely has a vector k coloring. Okay, so why are we going to this intermediate step involving vectors? Because we want to look at k colorings. We look at this thing called vector k colorings, but these vectors are more easily relatable to the optimization formulation that we had, okay, of the graph. So that's why we are going through this. So I'm calling it G prime. So let me continue calling it. If G prime has a K coloring, then I claim that it has a vector K coloring. Okay. So this is for K equal to 3. In general, you want minus 1 over K minus 1. So how do I show this? If G has a K coloring, it has a vector K coloring. Well, the construction is actually quite easy. Okay. So we want an assignment of set of vectors to every vertex in the graph such that for every edge in G prime, this angle is maintained. Okay. And what is the most natural thing to do? Well, notice what happens for K equal to 3. Let me just do this. For K equal to 3, if I have a 3 colorable graph, right? So you take that 3 coloring, okay? And now I need to assign vectors to vertices, right? So I'll just assign vectors in the two-dimensional space. The ambient space can be Rn, I don't care. But actually the solution vectors will lie in a two-dimensional subspace. And they will take only one of 3 values. I should not say 120 degrees. I just say 2 pi by 3. Makes more sense. Yeah. So these are my 3 vectors. And gamma of phi will be equal to, I'll call these vectors as say V1, V2, V3, right? And gamma of any vertex I is going to be equal to V chi of I. Okay. And I claim that this solves the problem for a 3 colorable graph. I have a vector assignment such that, why is that? Because for any edge in the graph, V prime in the graph, Vi transpose Vj is going to be, or sorry, gamma of I transpose gamma of j. Here all the red vertices will come, say, I suppose I'm using 3 colors, right? It's red, green, and blue. Right. Any vertex colored red is assigned V1. Any vertex colored green is assigned V3. Any vertex colored blue is assigned V2. Okay. If you take any edge, they will be assigned different colors across the edge, and therefore the inner product will be exactly minus 1 over half, or minus 1 over 3 minus 1, which is minus half. So that's fine. Right. So this is done. And the same thing can be generalized. Okay. If you have 4, right, then what do? You go to a regular simplex and take it. In general, you can set gamma of I to be equal to EI minus, or say, I'll take only k vectors, chi of I minus E. There are k colors to the graph divided by the norm. And we're just going to normalize it. Okay, this is in general for a k colorable graph. If you take this solution, it actually has the value claimed. So this I claim is now going to be, you can work out the inner products. This is going to be a feasible vector coloring. So now let me come back to what we have almost shown. I claim what we wanted to show. I'll take a couple more minutes. Uh, so we wanted to show that theta of G is less than equal to chi of G bar. Okay. Theta of G was this formulation problem. What is this optimization problem? Well, it was this minimization, right? Such that maybe Vi transpose Vj is equal to -1. Norm Vi squared is equal to t minus 1. Okay, so this was this optimization problem over the vectors Vi. Okay, we had shown at least half of the fact that this is equivalent. And we said that because chi of g is equal to k, then it has a vector k coloring. Okay, now what I'm going to do is I'm going to rephrase this problem as the following. I say that this is going to be equivalent to minimum over t such that Vi transpose Vj is -1 over t minus 1. I'm just scaling down the vectors, okay, by the factor t. So I say that it's equivalent to the following optimization problem, where you have unit vectors, and this is for all ij and e bar. Okay. So this is equivalent to the same problem. If you get VIs, if you get a solution for the first one, you can just scale it down by that factor t to get a solution to the second one of the same value, t. So I'm just scaling down the vectors, which is fine. The scale versions also are fine for this, right? So now, if you notice these constraints, this is exactly the constraint for having a vector t coloring, right? And we know that since it has a vector k coloring, right, and this is a minimization problem, this has to be less than equal to k. Because I'm giving you a feasible solution, which was constructed this way. So it has a vector k coloring. And that if you have a vector k coloring and you substitute it in, the objective value in that case is going to be equal to k, right? And this is a minimization. So this implies that the optimum is less than equal to k. Okay, and the optimum is nothing but theta of g. Okay, so what this shows via this optimization route is that theta of g is less than equal to the chromatic number of g complement. Okay, this is called as Lovasz sandwich theorem because it sandwiches the function theta of g between the chromatic number of g complement on one side and clique number of g complement on the lower end. Okay, so I had to skip some parts of the proof while doing this, but the key takeaway that I want you to remember from this is this idea that if you can formulate theta of g as an optimization problem, right? And once you formulate theta of g as an optimization problem, it gives an easy link into, say, the chromatic number on one side, the independence number on the other side. Okay. So what we'll do in the next part is actually going to look at other similar optimization formulations, okay, that have led to very nice approximation algorithms for problems. And we'll discuss just one such problem that also has a very geometric perspective on it. Okay, and you'll see how all of this, the main ideas of it were present in Lovasz's work, but it got exploited in the computational sense only later. Mhm. So I'll stop here. I'm a couple of minutes over time already. So I'll stop here and uh, willing to take questions the audience has any.
I just wanted to know what exactly is the interpretation of theta. I mean, is the minimum handle which holds all the
Yeah.
independent vectors?
So yeah, let's go back to theta. Maybe that's many slides before, but let me maybe create a separate. So theta of g is basically, if you look at orthonormal representations of the graph, right? So let me take it just from the geometric perspective. So theta of g is basically the value in some sense of the best representation you can find such that the vectors are all clustered around the handle C. Okay, you look at the inner products and it should be clustered around, and you take 1 over the uh, inner product squared. Right?
All the vectors or just the independent nodes or
No,
something?
all you're looking at all the vectors while evaluating the objective. So it's min over C. So you fix the handle C. With respect to the handle, it's max over I. Right. So it's 1 over C transpose UI squared, where I varies over everything. But the constraint is that if you look at the edge, the vectors that are in an independent set or don't have an edge between them, they should be orthonormal. So you cannot collapse everything to C and claim that, look, I'm getting a value of 1, because you need to at least spread out the vectors that have that form an independent set.
Okay, okay.
Now, one of the important things that we saw of theta of g from the other viewpoint is that it is an upper bound on the size of the independent set in power of the graph for any power. So this was the important thing that we showed yesterday. So it is related to independent set in the graph powers also in this way.
Are there other questions?